Think about this. Schools increasingly use AI, right, to spot students who might be heading down a difficult path. It's a powerful idea. But what's actually happening inside those AI systems, when a student gets flagged? What specific factors are raising those red flags?
Yeah, that's really the core of what we need to understand, isn't it? These predictive models, they're becoming more common in education. And it's crucial that we go beyond just knowing that a student is identified as at risk. We really need to dig into the why.
Exactly. And that's exactly what we're going to unpack today. We've got some really illuminating material here, almost like a blueprint, you could say,
Yeah.
for creating AI in education that's not only accurate, but also, and this is key, transparent, we're going under the hood.
Right. Our sources, they include some pretty detailed technical analysis of how these models can be explained, plus practical approaches for putting these explanations into practice, and even guidance on making the insights clear, clear and useful for teachers, for anyone involved in a student's education.
Okay, so our goal today, our mission for this deep dive, is to pull out the most important pieces from all of this. We want to give you a solid grasp of this concept called explainable AI, specifically as it applies to education, particularly when identifying students who might need extra support. We're aiming to skip the heavy jargon, focus on the essentials you need to understand, and, well, get you up to speed quickly. Okay, let's get into it.
Okay. Let's start with the basic idea, interpretability. Our sources really emphasize there are different ways to understand why an AI reaches a conclusion. We need to differentiate between sort of understanding the model's overall behavior, that's global interpretability, and understanding why it made a specific prediction for just one student. That's local interpretability.
I mean, when we're talking about something as sensitive as identifying a student as at risk, it really feels like that local, that individual understanding is the most critical part, doesn't it? It's not quite enough to know that, generally. Poor attendance links to higher risk. We need to know why this specific student right here was flagged.
Absolutely. You're talking about significant decisions, ones that can lead to interventions, maybe discussions with parents. They can really shift a student's learning journey. So yeah, we need clear reasons for each individual prediction. Our sources also talk about the difference between model-specific and model-agnostic ways to get that clarity.
Okay, can you break that down a bit? Model-specific versus model-agnostic.
Yeah.
What do those mean in practice?
Sure. So model-specific methods, they're basically built into how a particular type of AI model works. For instance, let's say a school uses a decision tree model. You can actually visualize the entire tree structure, see the exact rules the model uses. That's a global model-specific view.
Right, you see the whole map.
Exactly. And then for a single student, you could trace their data right through that tree. See the specific path that led to their risk score. That would be local and model specific.
Okay, that makes sense. So then, what are model-agnostic methods all about? Are they just generic?
Kind of. They treat the AI model more like a black box. They can explain the predictions of any model, basically. They just look at what goes in the student's data and what comes out the risk prediction. A global model-agnostic example. Something called partial dependence plots, PDPs. These show the average impact of one factor, let's say attendance, on the predicted risk across all students. And you don't need to know the inner workings of the AI model itself.
Got it. So PDPs give the big picture trend for one factor, and for getting those local, individual explanations with this model-agnostic approach.
That's where tools like Lime and Esheep come in. They're really key here. Lime, it works by creating a simpler, sort of understandable model just around a single prediction. It helps pinpoint which features were most influential just for that specific case.
Okay, a local approximation.
Exactly. And S-shape, that stands for Shapley Additive Explanations, it uses ideas from game theory, actually. It assigns a value to each feature, showing how much it contributed, positively or negatively, to a specific prediction.
Game theory. Interesting.
Yeah. And these tools are incredibly valuable because you can use them even on very complex models, or maybe proprietary ones where you can't see inside.
Okay, tell us more. Let's talk about these tools in action, like in a school setting. What does it look like?
Okay, so our sources highlight several key ones. Let's dive into SHA first. Technically, SHAP gives us this value for each piece of student data, like attendance, grades, whatever. And that value shows how much that specific piece pushed the AI's prediction up towards at risk or down away from it for that one student.
Ah, okay. So if a student's flagged high risk, SHAP could tell us, was it mostly attendance? Or maybe low grades in one subject? Or a mix.
Precisely. And globally, across all students, SHAP can generate something called a beeswarm plot.
A beeswarm plot.
Yeah, imagine a swarm of dots for each factor, like attendance or GPA. It shows the range of impact that factor has. You might see, generally, good attendance pushes the risk score lower. Maybe those dots are blue and on the left, while poor attendance pushes it higher, red dots on the right.
Okay, I can picture that.
And then, for an individual student, SAP can create what's called a force plot. Think of it like a visual tug-of-war. Each factor is an arrow pushing the risk score higher, red arrows, or lower, blue arrows.
Oh, nice.
So a long red arrow for many absences would show a strong push towards at risk, but maybe a smaller blue arrow for good test scores would show it pulling back a bit. Imagine how useful that is for a teacher talking to a parent instead of just, well, the system flagged them.
Right, much more concrete.
Exactly. They can point to the specific factors the AI highlighted as most critical. It grounds the whole conversation in data.
That visual sounds incredibly helpful, especially for someone who isn't a data expert. What about LIME? You mentioned LIME. How did that work?
Right, LIME. Local interpretable model agnostic explanations. It takes a slightly different approach. For one specific student's prediction, LIME builds a temporary, simple, easy-to-understand model, like a basic linear model. It acts as an approximation of the complex AI, but only in the neighborhood of that specific student's data.
So it zooms in locally.
Exactly. So if a student is flagged high risk, LIME might reveal that, for them, maybe a big drop in their last math grade was the biggest factor pushing the risk up, followed maybe by a drop in class participation. It creates this simple, tailored explanation just for that one case.
Okay, so SAPE uses game theory for contribution values. LIME builds a local simplified model. What other tools should we know about?
Well, there's ELI5, which kind of amusingly stands for Explain Like I'm 5.
Ah,
It's a useful tool, provides a consistent way to get explanations from various models. For simpler models, like linear regression, it can directly show you the weight or influence of each factor. For more complex ones, it might use other techniques, maybe even calling SIP or LIME under the hood sometimes. And then we have those partial dependence plots, PDPs, we touched on earlier.
right, the average trends.
Yeah, they show the average impact of a single factor, like attendance, across all students. So a PDP might show a curve. As attendance improves, the average predicted risk goes down.
Okay, so PDP gives the general trend. How does IC fit in? I think you mentioned ICE plots.
Good catch. IC stands for Individual Conditional Expectation. ICPs take it a step further than PDPs. Instead of just the average effect, an ICE plot shows the effect for each individual student.
Whoa, okay.
So on an IC plot for attendance, you'd see a separate line for every single student, showing how their predicted risk changes as you hypothetically tweak their attendance. It's really valuable for spotting if a factor affects different groups of students differently. You might see clusters of lines behaving differently.
That sounds like it could uncover some really important nuances. But I guess each tool probably has its pros and cons.
Absolutely, yeah. There's no single perfect tool. SEGP, for instance, is very robust, has that strong theoretical backing we mentioned, but it can be computationally expensive, especially kernel chap, the version that works on any model. It can take time to run.
Okay, so powerful but potentially slow.
Right. LIME is often more intuitive, easier to grasp initially, and handles different data types well, but its explanations can sometimes be a bit unstable. Run it twice on the same prediction, you might get slightly different feature importances.
Okay, consistency issues, potentially.
Potentially, yes. ELI5 is great for quick insights, especially from simpler models, but might not give the depth you get from SAT on complex ones. PDPs are good for overall trends, but can totally mask individual differences, which is where ICE comes in.
But ICE plots could get messy with lots of students.
Exactly. They can become a bit of a spaghetti monster if you plot too many lines. Our sources actually have a helpful table summarizing these trade-offs.
And compatibility.
Yeah.
Do they all play nice with different AI models, like linear trees, neural networks?
Good question. Not universally. SAP has specific explainer versions optimized for different model types. Like Tree Explainer is super fast and accurate for tree-based models, things like XGBoost, random forests, which are very common for this kind of structured student data.
Ah, so it's tailored.
Right. Then there's Kernel Explainer, which is the general model-agnostic one, but slower. Linear Explainer for linear models, Deep Explainer for neural networks. LIME is generally model-agnostic. ELI5 supports many common models, especially from libraries like scikit-learn and tree ensembles. But it's worth highlighting that SAP's Tree Explainer is often a really strong choice for the models typically used in student risk prediction.
You mentioned wanting to do a deeper dive specifically on SAP. What makes it stand out so much in this context?
Well, it's that combination of the strong theoretical foundation, the Shapley values from game theory, and its versatility. It offers a consistent way to measure feature importance, both globally for the whole model and locally for each prediction. And as we just discussed, it has these different explainers optimized for specific model types, which is really practical.
Like the tree explainer for the common tree models.
Exactly. That makes it fast and accurate for many relevant use cases, and kernel explainer gives you that model agnostic fallback, even if it's slower.
And it handles the typical kinds of student data, okay? Numbers, categories.
Yes, it handles numerical data like grades or scores, and categorical data like, say, participation in programs. While there are SHIP extensions for text or images, they're less common in standard risk prediction using structured data tables. One technical point to be aware of, though, is that standard SHAP often assumes features are independent.
Independent. But things like attendance and grades might be related, right?
Precisely. Poor attendance might often go hand in hand with lower grades. They're correlated. SHAP's basic assumption of independence can sometimes lead to slightly misleading importance values for correlated features. There are advanced ways to handle this, like using interventional modes in Tree Explainer, but it's something to keep in mind.
Okay, good caveat.
Okay.
And visually, how do we actually see these SHAP outputs? You mentioned beeswarms and force plots.
Yes, the visualizations are a huge strength. Beeswarm plot gives that great global overview. You see immediately which factors generally push risk up or down and how much spread there is.
Right, the overall impact.
And the force plot is fantastic for explaining a single prediction. That visual tug of war showing how each feature for that specific student contributes to their final risk score relative to the average.
Yeah, that seems super useful for communication.
Absolutely. It makes the why much more tangible for people who aren't data scientists.
Now, there's always this trade-off, isn't there, between performance and interpretability. You could have a super complex AI, maybe really accurate, but it's a total black box, or a simple model, easy to explain, but maybe less accurate at finding the students who really need help.
Yeah.
How does this balance play out in education AI?
That is a really, really critical point. It's a constant tension. Simpler models like logistic regression or basic decision trees are often inherently interpretable. You can often look directly at their structure or coefficients and understand the logic.
Makes sense.
But they might struggle to capture the really complex, subtle patterns in student data compared to, say, an XGBoost model or a neural network, which potentially means lower predictive accuracy.
Our sources mentioned a specific comparison, I think. Logistic regression versus XGBoost. What did that show?
Yeah, that's right. The source cited a study where XGBoost achieved a noticeably higher AUC score, around 0.86 compared to logistic regression, which was about 0.77.
And AUC measures how well it distinguishes between at risk and not at risk. Higher is better.
Exactly. Closer to 1 is better. So XGBoost was significantly better at identifying the at-risk students in that case. But that accuracy came at the cost of inherent interpretability. Logistic regression coefficients are relatively straightforward to explain. Explaining XGBoost requires those post hoc methods, like SHAP that we've been discussing.
So the question becomes, is that accuracy bump worth the extra complexity and the need for these separate explanation tools?
Precisely. And it's not just XGBoost versus logistic regression. The same trade-off exists elsewhere, like a simple interpretable decision tree versus a potentially more accurate but opaque neural network.
So what strategies can schools or developers use to find a good balance?
Well, one strategy is exactly what we've been talking about. Use a high-performing complex model, but then layer on post hoc explanation tools like SHAP to understand its decisions.
Okay, explain the black box after the fact.
Right. Another approach is to use hybrid models, maybe combining simpler interpretable components with more complex ones. Or focus heavily on feature engineering, carefully selecting and crafting the input data so that even simpler, more interpretable models can achieve good performance.
So better data might let you use a simpler, clearer model effectively.
Effectively. And especially in student risk prediction, both accuracy and clarity are vital. You need to find the right kids, but you also need to understand why they were flagged to help them appropriately and build trust. Sometimes research points to this idea of a flat maximum too.
Flat maximum.
Yeah, where several different models, some simple, some complex, all achieve very similar, near optimal performance levels. In that situation, it might make a lot of sense to lean towards the more interpretable option if the accuracy difference is negligible.
Makes sense. Choose clarity if performance is roughly equal. Okay, this gives a great picture of the current state. But looking ahead, generative AI, It's everywhere now. How might something like, say, GPT-4 fit into making educational AI more understandable?
Yeah, this is a really exciting and rapidly developing area. Our sources definitely touch on this. The idea is that a powerful language model like GPT-4 can take the somewhat technical output from explainability tools like those SHA values or LIME outputs and translate them into natural language explanations. Explanations that are much easier for educators, parents, or even students themselves to understand.
Whoa. So instead of a teacher deciphering a forest plot, they could get a clear, written paragraph explaining why a student was flagged.
Exactly that. The process would involve feeding the structured information from the explainer tool, maybe the top 3 to 5 factors and their SHA values into GPT-4. But crucially, you feed it in with a very carefully designed prompt.
A prompt like instructions for the AI.
Precisely. The prompt tells GPT-4 what role to play, maybe. You are a helpful educational advisor. It provides the specific student data and SHA values, and it specifies how the explanation should be written, the tone, the length, maybe even a specific structure.
What are the key things for crafting those prompts effectively?
Clarity and constraints are vital. You need to instruct GPT-4 very clearly to only use the information provided.
Stop it from making things up.
Exactly. Prevent hallucination. You also guide the tone. Make it informative, supportive, professional. Avoid blame or overly alarming language. You might even give it an output template, like write a 5-sentence summary. Sentence 1 states the prediction. Sentences 2-3 list factors increasing risk. Sentences 4 top list factors decreasing risk.
That level of structure sounds really helpful for consistency.
It is, and it can really bridge that gap between the technical AI output and the practical understanding needed by educators.
Okay, so let's imagine putting this all together. In a real school setting, what might the day-to-day process look like?
Well, our sources sketch out a potential production pipeline. It could look something like this. First, the AI model makes its risk prediction for a student. Second, an explainability tool like SHAP analyzes that prediction, calculating the feature contributions. Third, those SHAP values and key features are fed into GPT-4 with a structured prompt. Fourth, GPT-4 generates the natural language explanation. And finally, all of this, the prediction, maybe a SHAP visual, and the GPT-4 explanation is presented on a dashboard for the educator.
Wow. So teacher logs in, sees maybe a list of students flagged, clicks on one, and gets the score, the why in numbers or visuals, and a plain English summary.
That's the vision, yes. And the system needs built-in smarts to handle tricky cases, like what if the prediction confidence is low, or what if there's lots of missing data for a student?
Right. The explanation should reflect that uncertainty.
Exactly. The explanation might need to include caveats like prediction based on limited data or factors pointing in both directions. And for the data scientists building these systems, the sources emphasize things like automation, strong security, detailed logging, and crucially, building in feedback mechanisms.
That feedback loop seems absolutely essential, doesn't it? To make sure this is actually working and helpful.
Couldn't agree more. You need educators to be able to easily provide feedback. Was this explanation clear? Did this prediction seem accurate? Was this useful for planning support? That human-in-the-loop input is invaluable for refining the AI model itself, the SHAP analysis, and the GPT-4 prompts and outputs. Plus, you absolutely want to track student outcomes over the long term. Are the interventions informed by these AI insights actually making a positive difference? That's the ultimate test.
Okay, so wrapping things up a bit, based on everything we've covered from these sources, what are the key technical takeaways, the recommendations for doing this effectively?
Yeah, the sources offer some solid practical advice. For typical structured student data grades, attendance, demographics, etc., the combination of a tree-based ensemble model like XGBoost or Random Forest paired with SAP's Tree Explainer often hits a sweet spot.
Why that combo specifically?
Because it tends to provide high predictive accuracy, while Tree Explainer offers efficient and accurate explanations for those specific model types. It's a good balance. Now, for simpler scenarios, maybe as a starting point, logistic regression explained with ELI 5 could be perfectly adequate. The main thing is to choose your tools based on both your performance needs and your explanation goals.
So if you absolutely need top accuracy and use a complex model,
then you must invest in robust post-hoc explanation methods. Maybe even using multiple tools like SHAT and LIME for different perspectives, and leveraging something like GPT-4 to synthesize those explanations into something easily digestible becomes even more critical.
Right, and this isn't a set it and forget it kind of thing, is it? What about long-term management?
Absolutely not. Long-term maintainability is huge. That means having processes for regularly retraining the model with fresh data, keeping meticulous documentation, continuously monitoring for performance drift or emerging biases, ensuring the system can scale, maintaining the integrations with other school systems, and critically, providing ongoing training and support for the educators using it. Oh, and let's not forget privacy and ethics oversight. That needs to be woven through the entire life cycle.
This has been a really, really insightful deep dive. It's so clear that while AI holds immense promise for education, especially for helping students who might struggle, that ability to understand why the AI reaches a conclusion is not just nice to have, it's absolutely essential. It's about trust, effectiveness, fairness.
Absolutely. It's about finding that careful balance between model performance and interpretability. And by thoughtfully choosing and combining tools with SHA playing a key role, and maybe generative AI like GPT-4 helping with communication, we can actually build these more transparent, trustworthy systems. Systems that truly empower educators to give better, more targeted support.
So as you, our listener, reflect on all this, maybe think about how these techniques for making AI understandable might keep evolving. How could they further personalize student support down the line? And perhaps also consider the responsibility that comes with using these powerful tools, the responsibility to demand transparency, to understand the why, and to explain it effectively. It's definitely a lot to think about, and we really hope this deep dive has given you a valuable foundation for exploring these important questions further.